Okay, hi everyone. Let's go ahead and get started with today's lecture. So today is lecture 5 for our course on machine learning. And so today we'll be talking about a topic called model selection and regularization. And before we begin, I'd really like to emphasize that a lot of the ideas and methods here that we'll be talking about today really apply to machine learning models in general, not just regression algorithms. So later in the course, when we talk about things like classification, you should keep in mind these techniques for model selection. They'll still apply just to different types of models. Okay, so before we get started, just a couple of announcements. Discussion sections are tomorrow. This week's discussion will be covering matplotlib and scikit-learn, so I'll give you guys some demonstrations, some more examples of how to use these packages. You should also come prepared to the discussion section, so if you have questions about lecture or homework or machine learning in general, the discussion section is a really good time for you to interact with the TAs and ask them any questions you might have about the course. The first homework, as I'm sure you are all aware of, is due on Friday. It's due at midnight on Friday. Keep in mind, we don't accept late homeworks for this course. It's a big class, and trying to keep track of these would be a bit of a headache. But we do drop your lowest homework score, so if you aren't able to complete homework 1 on time, you'll have the other 4 homeworks to make up for it. Again, you should submit a PDF of your homework via Gradescope. It's important that we can see all of your answers, see all of your graphs, otherwise we won't be able to actually grade your assignment. If you're having any trouble with actually creating this PDF or submitting it, please do post on Ed. You can get some help there. At the very bottom of the homework, there's a question about a statement of collaboration that we've gotten a few questions about. This is essentially 5 free points on the homework. And all you got to do for this is essentially, if you worked with anyone, just write the names of the people you worked with. If you looked at any online resources, just list these there for that question. But if you completed the homework totally on your own, which good for you, good job, make sure you just state this, say something like, yeah, I didn't use any external resources. And then the second homework for the course is going to be released early next week, so keep an eye out for an announcement about this. Should be out roughly around Monday, hopefully before the lecture. So any brief admin logistic questions before we get started? Cool. So in today's lecture, we'll cover 3 topics. The first is model selection, essentially, how do we pick which machine learning model we're actually going to go ahead and deploy on our problem? The second topic we'll cover is cross-validation, which is a method we can use to actually do model selection. And lastly, we'll talk about a technique called regularization, which is one way that we can try and prevent overfitting in a machine learning model. So before we get started with model selection, just a few reminders of nonlinear regression from the previous lecture. The basic idea in nonlinear regression is that if we have some feature vector with d different features, so here's our feature vector, we can compute what's called a feature expansion of this feature vector, which is just some transformation of our data. In this case, we might consider a polynomial feature expansion. So we essentially take all the different powers and different combinations of our features. And then to do nonlinear regression, we just fit a linear model on top of these new polynomial features. So again, we'll have to first fix a polynomial degree p to do nonlinear regression, compute these feature expansions, which you can do fairly straightforwardly in scikit-learn, then fit a linear regression model on top of these new features, as I was saying. And again, you can just use the scikit-learn packages to do this. And in problem 3 of the homework, you'll be using exactly these methods here in order to help you complete that. A brief reminder on overfitting and underfitting. The basic idea you should keep in mind for this topic is that the complexity of a model should somehow match the complexity of a data. For underfitting, our model is too simple to actually model the trend in the data. So this is like fitting a line to a nonlinear data set. In overfitting, our model might be too complex. It fits the data so well that it can't generalize to new data that we didn't see during training. And this is like fitting, say, a 15-degree polynomial to this small data set that we have. And one of the key questions we need to ask ourselves in nonlinear regression is, what polynomial degree should we actually use? So the degree of this polynomial is, again, it's a hyperparameter. It's not something that's learned from data. It's something we need to pick when we're writing down our model. One way we can detect overfitting and underfitting is by looking at the performance of our model on training data versus data that it didn't see during training. So all of the blue dots are points that the models actually fit on, so we train on the blue data. And all the red dots are points that the model didn't see during training, so this is kind of held out test data. And what you should see is that as we get a better and better fit, the MSE on the blue data goes down, so we fit our training data better. But the testing MSE, the red MSE here, actually increases when we start to overfit. So this is one way you might be able to actually detect under and overfitting. Okay, so the question you should keep in mind for model selection now is how do we actually pick that degree of that polynomial? You know, how do we choose what polynomial to use? And one very common but straightforward technique for actually doing model selection is to create what's called a train validation test split of your data. So the idea here is we take our data set, some big data set we have, and we might say take 70% of this data and split it off into a training set. We can take another 15% of this data and create a new subset, which we can call our validation set. Also sometimes called like a dev set or a development set. And then with the remaining 15% of our data, we can take that 15% and create a third subset of our data called the test set. On our training set, what we're going to do is we're going to train many different models on this set of data. So you might fit a linear model, a quadratic model, you know, so on and so forth, many different polynomials, all on this same fixed training set. You can also vary things like, say, the learning rate if you're using gradient descent and other various hyperparameters in your model. Later on, when we see more models beyond just regression models, you can also, you know, try out different algorithms for your data. But the idea is we're going to train all of our models on this training set. On our second subset here, the validation set, what we're going to do is we're going to take the models that we trained on the training set and evaluate them on this kind of held out validation set. So this is data that the model didn't see during training, and in some sense it's simulating what would happen in the real world. We train a model on some data that we have, and then we go out and deploy it on some new data that comes to us sort of from the real world, and we'd like to see how our model is going to perform. Then using the performance of our models on this validation set, we can actually assess if our model is, say, overfitting or underfitting, and whichever model is performing best on this validation set then, we can then sort of select the best model. And after we've selected the best model using this train validation procedure, we can then finally actually evaluate the performance of that final model on this third held out test set. And we'll see in a little bit why you actually need a third test set, why you can't just have a train set and a validation set. So a couple of notes on creating these train validation test splits. The first is that the percentages I'm giving here, this 70, 15, 15, they're just heuristics, just rules of thumb. You might see something like 80, 10, 10 as another pretty common way of splitting your data. But you know, it's really up to you when you're doing your machine learning tasks, how you decide to do these splits. If you have a very, very large data set, like let's say you have 1 million data points, well, spending 15% of those 1 million data points on validation and another 15% on test might be a little bit overkill. You know, we don't need 100,000 data points to evaluate our model on. And in some sense, you want your training set to be as large as possible because, you know, more data means better models at the end of the day. So again, these percentages, just rules of thumb, they're not sort of hard and fast rules. A really key component to be aware of here is that it's absolutely critical that you have no overlap between these 3 data sets. So if somehow in your code there's, say, a bug in your pipeline, if some of your validation data also shows up in your training data, you've got a problem called data leakage. Essentially, you're kind of cheating because you're training on data that you then evaluate on your validation set, which is really meant to be held out. It's not meant to be seen by the model during training. Oftentimes, you can detect a data leakage problem is if you have an overly optimistic evaluation of your model. So this is a real problem that happens in machine learning. So, for example, I was working on a research project once, and I trained a model, evaluated it on my validation set, and got like 98% accuracy, and I was like, oh, great, something really worked finally. But it turns out I had some data leakage, and I was actually training on data that appeared in my validation set. So very real problem, and something definitely to be aware of. As I mentioned before, your validation and test sets just need to be kind of sufficiently large to have a good evaluation. If you have too few data points in your validation set or your testing set, when you go to evaluate your models on these subsets, you're going to get a noisy, unreliable estimate of the error. So, for example, imagine your validation set had only 25 data points. Well, if you're evaluating your error on just 25 data points, it's not going to be a very reliable estimate of that error. So, again, you don't need to make these 15% of your data, but just large enough that you get a reliable estimate of your error. Again, scikit-learn does most of what we want it to do in machine learning. So there's some nice tools here to create these train test splits, just coming straight from sklearn. This function here will create just one split of the data, so it might take your data and make a train set and a validation set. And if you want to make a third split, you'll probably need to call this function twice. So you can make a train set and a val set, then split the validation set a second time. Another piece of advice when you're making these splits of your data is that in scikit-learn, there's this keyword for this function here called shuffle. And what this does is it takes your data and just randomizes the order of your data before actually creating these splits. And you almost always want to shuffle your data before you actually use it in a machine learning pipeline. So for example, some data sets, just because of how they're collected or formatted, might be ordered in some kind of pathological way. So for instance, they might be ordered by the Y value in a regression problem. And if you don't shuffle your data, then maybe all of the values with small y end up in training, and then all of the values with large y end up in your test sets. And this can lead to just biased estimates of the model performance. Okay, so as I promised, I'll answer the question why we actually need a separate test set instead of just a validation set. And the idea is that the performance on the validation set is actually going to influence the choice of model. So, maybe for an analogy, imagine your training set is like lectures for some course you're taking. And if you're taking an exam for a class, you can go and study the lectures, the training set. It's all, the information available to you. The validation set then is like maybe practice exams. You can take the exam, see how well you do on those practice exams, then kind of, adjust your studying based on those exams. The test set then is kind of the real exam. We aren't allowed to look at this test set and adjust our models at all. In some sense, you can overfit to the validation set if you don't have this third held out test set. And again, the idea of the test set is we really, really want to simulate what our model's going to do when we apply it to data we haven't seen at all previously. Okay, I think I showed this slide on Monday, but if we want to assess how well our model is doing, kind of a key way of doing so is trying to figure out if it's overfitting or underfitting. And using this kind of paradigm of train validation splits, we can assess this over-underfitting regime. So if we have high error on our validation set and high training error, that means we're not even doing good on our training data, and so we're underfitting. If we have low training error but very high validation error, then we're in this kind of overfitting regime, where we do well on data we saw, but not well on data we didn't see before. If you're in this bottom right corner where you have low validation and low training error, then you're doing a good job with your machine learning project. And if you end up in this bottom left corner, probably something went wrong. One thing I'll note is that sometimes it can be too expensive to just train 1,000 models from the get-go. So you might want to train all your models and then evaluate them all on the validation set afterwards. But this can be really expensive if you have a model that takes a long time to train. So something like a large neural network, like what we'll work with later in the course, it might take a couple days, a couple weeks, maybe even a month to train some of these large networks. And so you can't possibly train, thousands and thousands of different models and then go and evaluate them afterwards. So one thing you can do instead is train a model, look at its performance on the validation set, use this kind of heuristic table here to guide changes that you'd like to make to your model. So let's say we train a really big model, evaluate it, and say, oh, look, it's underfitting to my data. That means I need to make my model more complex, so I can make some changes to my model, retrain it on the data set, and then evaluate again. So in other words, you can do a sort of iterative process where you kind of bounce back and forth between training and validation rather than doing all your training and then all your evaluation at once. Okay, I'd like to show you guys a figure here, just giving you some more intuition to keep in mind on this sort of overfitting, underfitting trade-off. So on the x-axis here, I have some measure of model complexity. Maybe this is like the degree of a polynomial that I'm fitting to a regression problem. And on the y-axis, I have some measure of loss or some measure of error, maybe the mean squared error. In the red curve, I'm plotting the error rate on the training data. And what you should notice is that as I increase the model complexity, the error in my training data is going to decrease. And this should make sense. If I make my model bigger and better, it's going to do a whole lot better on the data that it actually saw. But interestingly, the error on the validation data, or the error on your testing data, will decrease for a little while, and then eventually start increasing. And that's exactly that overfitting problem that we've been talking about. So on the left-hand side of this figure here, you're underfitting if the error on both of your sets is quite high. You're in this overfitting regime if the error on your training data is low, but the error on your validation data is high. And somewhere in the middle here is sort of the ideal range for model complexity. So generally this graph isn't super useful in practice to actually assess over and underfitting, but it's good to keep this concept in mind. Okay, so far I've talked about this train validation test split, and using this to somehow select the best model out of multiple choices. But how do we actually evaluate a model on the validation set? How do we pick which model is sort of best? For a regression problem, the most straightforward thing you can do is just look at the loss function, so the mean squared error. So you can look at the mean squared error on the training set and the testing set and use this to do model selection. But evaluation of your model doesn't need to be limited just to the mean squared error loss function. You could look at, say, other metrics like r squared. So if you guys have done regression in the past, you might have heard of this metric. So r squared is just 1 minus the mean squared error divided by the variance of your y variables. And essentially this measures sort of how much variation in the y variables is captured by your regression model. One of the benefits of using r squared over mean squared error is that r squared is always between 0 and 1, so it's a little bit easier to interpret, whereas mean squared error can be sort of any arbitrary positive number. Another thing you might like to assess when you're evaluating models is how fast does our model actually train? So if you have a really simple model that trains quickly and gets decent performance, or a very large model that takes days to train but gets slightly better performance, you might want to keep this trade-off in mind. The best performing model might not be the one you actually want to use in practice. There might be concerns like training time here. For example, you might want to retrain your model if you go out and collect new data, and doing that on a simple model is going to be a whole lot easier than a very complex model. Another question you might ask yourself when you're evaluating your models is, how fast is prediction with the model? For some problems, you might actually need real-time predictions from your model. There might be time constraints. So, for example, in an autonomous vehicle, you don't want your car to be taking 5 seconds to predict whether or not it should turn left or turn right. It's just not going to be quick enough for what you want to do. So even though you might have a better model, it might be a slower model. So this is another thing you should keep in mind when you're evaluating your models and kind of choosing which is best. Another thing you might consider is how much memory the model requires. So if you're deploying a machine learning model, say, on your phone, you can't have as powerful a model as you could if you were deploying it on a supercomputer somewhere. So you should keep in mind also, these kinds of memory requirements. Another aspect you should consider is sort of the fairness of the model. We haven't talked a whole lot about sort of fairness and bias. We introduced these concepts in sort of lecture 1, but it's another thing that you can kind of evaluate for your model before you go ahead and deploy it. Okay, so any questions on this model selection framework? Yeah. Yeah, exactly. You want your error on the validation data to be as small as possible. It's going to generally decrease and then start increasing when you start overfitting. And so the slope should probably be 0 here. Yeah, exactly. Cool, other questions on model selection? Yeah. It depends on your problem. Maybe something like 10,000 data points might be sufficient. If you really want to be kind of rigorous about it, you'd like to be able to do like statistical tests and say, okay, if I have this much data in my test set, I know the error within some bound on that error. So you can be a little rigorous with how you pick these numbers, but yeah, ballpark like 10,000 data points if you have a massive, massive training set. Cool. I'll point out here that there's a whole host of more advanced model selection methods, but for all intents and purposes, this train validation test split is what most machine learning practitioners do. Yeah, another question. Mm-hmm. Yeah, so R squared is a number between 0 and 1. 0 means your model is absolute garbage, and 1 means your model is perfectly fitting the data. So in some sense, it's the same idea as MSE. It's measuring goodness of fit, but it's kind of normalized to be between 0 and 1. And really what it's doing is, in some sense, measuring how much of the variance in the y variable is captured by the model. So if you have, say, a quadratic and you fit a line to it, there's a lot of variance in the y that the model just isn't picking up on because it's sort of too simple. So for all intents and purposes, it's a normalized version of the MSE. Okay, let's go ahead and move on to cross-validation. So this train validation test idea is really great. Most people in machine learning use this. But what if we don't have a lot of data? What if we have 20 data points or 100 data points? Well, splitting our data into a train set, a validation set, and a testing set is going to be problematic. We just don't have enough data in our training set then to fit a good model. We don't have enough data in our validation sets to evaluate that model accurately. So we're going to need to do something a little bit different here. What we can do is called k-fold cross-validation. It's a fancy name for something that I think is a fairly intuitive technique. What we're going to do is we're going to create multiple validation sets from our data, train on the things that are not in each validation set, and then average over these different splits that we create. And so we'll see some examples of this if it's not totally clear yet. So for example, in a 10-fold cross-validation, we'll first randomly divide our data into 10 disjoint subsets, or folds as they're commonly called, each of these folds having 10% of our total data set. So we make 10 disjoint bins in our data. Then for each of the 10 folds, we'll train a model on 90% of the data, and then evaluate on 10% of the data. Then we kind of choose which fold is the validation set, over each of these 10 possible splits and average over all of the possible errors. Again, this is a very general purpose technique for sort of model evaluation. It's not limited just to regression. We'll also see it applied to classification models in a little bit. But one of the downsides of doing this is it actually requires training k different models, where again, k is the number of folds, in order to do just one evaluation. So for example, if I want to evaluate 10 different polynomial degrees, I would have to train 10 times k different models in order to use cross-validation. Okay, let's see an illustration to make this a little more concrete. We might have our original data, which for all intents and purposes, we can think of as just indexes into some data matrix. So the first index is, of course, 1, and then 2, 3, and so forth. We'll shuffle our data, which is the same as just shuffling the indices. So this solves that kind of sorting problem that I brought up before. We're going to create 5 folds, where on each fold, we train on 80% of the data and evaluate on the remaining 20%. So our first fold is 20% of the data. This is like a validation set almost. Then we train on the remaining 80% of the data. So we train on the orange bit, evaluate on the blue bit. We kind of move our fold over one step. So we train on all the orange bits of our data and evaluate on the blue bit. Same idea for the third fold, the fourth fold, and the fifth fold. So in some sense, we're like simulating having multiple different validation sets. Is this clear enough? I can take maybe 1 or 2 questions if it's not. Exactly, yeah. So we're using our data for both validation and training, but we never evaluate on the data that we train on. Yeah. So we're not like creating new data or anything like that. It's like if we had 5 different train validation splits almost. It's just a way of sort of simulating what it would be like if we had multiple training sets. Okay, let's see an example. So let's say we're doing cross-validation for regression, where we have a tiny data set with only 9 data points. And what we'd like to do is compare a degree 1 polynomial, so a linear regression model, with a degree 3 polynomial model. Here's my training data on the right-hand side. So the gray is sort of the training split for cross-validation. The green is the validation split for cross-validation. So you should see it's a third of our data. On the first split, we train on the gray data points and evaluate on the green data points. And the evaluation on the green data points gives us an MSE of like 330. Okay, we now move our split. We have a different validation set, get a different MSE. And then in our final split, we have again a different MSE. And then what we do is we average all of these different MSE values to get a final cross-validation MSE of 464 here. We do the same thing then with our third order polynomial, so our different model. So in our first split, we get an MSE of 280, then an MSE of 3,000, and then finally an MSE of about 1,600. We average these numbers, get a cross-validation MSE of about 1,600. And then based on this evaluation, we should probably pick the linear model over the degree 3 model because it had a lower cross-validation error. And again, we're doing this because our trained validation test paradigm that we introduced before just isn't going to work when we only have 9 data points. We just don't have enough data to reliably estimate these MSEs. For example, on these 3 different splits, the values of the MSEs are wildly different between 280 and 3,000. So having a very small validation set, we get noisy estimates of the model performance. Cross-validation is straightforward enough to do in scikit-learn. So we've got this k-fold function that will actually do these splits for you. There's another thing in scikit-learn that I'll point out called leave one out cross-validation. This is a special case of cross-validation where the number of folds is actually equal to the number of data points. So if we have n data points, on each of our splits, we'll fit a model on n minus 1 of the data points and evaluate on only a single data point, and then average all of these. Leave one out, cross-validation is mostly useful for very, very small data sets because, we're going to have to train a total of n models, so it can be very expensive. But it's most useful when you have a really tiny data set that you're trying to evaluate on. An alternative method to cross-validation for doing model evaluation with limited data is called bootstrapping. It's a similar idea where we're kind of simulating having multiple training test splits. And the idea is if we have n data points, we can create a total of capital M new training validation sets, where essentially we do a for loop from I equals 1 up to m, where we create a training set by sampling from our data set with replacement. And we'll sample the same number of data points as in our original data set. So it's like we're creating a new training set by simulation. Again, here's the scikit-learn function that'll help you do that. We then can create a validation set by taking all the data points that are not in this new training set that we create by sampling. And then similar to cross-validation, we'll fit the models on the training sets, evaluate on these validation sets, and then average over all of our capital M bootstraps. Both bootstrapping and cross-validation are widely used in practice. Bootstrapping is a little more popular in the statistics literature, but cross-validation is more popular with the machine learning folk. I'll point out that cross-validation, one reason you might not want to use it is that you're actually training models on smaller data sets than your full training set. This is because we need to split away part of our data for those validation sets. As a result, you can actually underestimate your model performance if you're using cross-validation because you're just training it on less data. In contrast with bootstrapping, when we create these new data sets, we're always creating a new data set that has the same number of data points as our original data set. And therefore, we're always training on sort of the same amount of data. Cross-validation can also be thought of as very similar to bootstrapping, except we're just sampling without replacement. So one of the key things in bootstrapping is this with replacement step. So our data points can actually show up multiple times in these new training sets that we create. For all intents and purposes, cross-validation is the go-to technique in machine learning. And I mostly point out bootstrapping here because we'll see it later in the course to develop a couple of techniques called ensemble methods. So it's good to have at least heard of these bootstrapping methods. Okay, any questions on cross-validation or bootstrapping? Okay, if not, we can move on to the final topic in today's lecture, which is regularization. Okay, so let's, for example, say we're fitting a linear regression model on a feature vector with d different features. So we've got parameters theta 0, theta 1, all the way up to theta d. And this is just our usual linear regression model that we've seen a couple times now. This model is learned by minimizing the mean squared error. So our loss function, L of theta, is this MSE function. And recall that your intuition about overfitting should be that it happens when our model is somehow too complex for the data set. And so an interesting question is, can we somehow measure the complexity of our model? Can we assign a number to this parameter vector that tells us how complex that model is? And you can maybe think about this for a second before I give away the answer. But let's suppose we could somehow do this. Suppose we could write down a function, which I'll call r of theta. This function r of theta takes in our parameter vector theta and spits out just some number measuring how complex that model is with those parameters theta. So the idea is if r of theta is some high number, our model has high complexity. And if r of theta has a low value, then our model has low complexity somehow. What we can do is if we have some kind of complexity function, r of theta, we can use it to regularize our model. In order to do so, we're going to essentially add this complexity penalty into our loss function. Okay, so let's see what that looks like in the context of MSE and regression. So I'm going to define a new loss function, L sub r of theta. Again, this is some function measuring how good of a fit our model is to the data. And this new loss function is the MSE loss function, so just the usual thing. plus alpha, which is some scalar, times this complexity measure r of theta. So we've created a new loss function that's a combination of the MSE and of this complexity function. Writing out the MSE, this is the same thing I had on the previous line. And the idea here is that this new loss function, L of r, is something, again, that we would like to minimize, just like how we would like to minimize the MSE for regression. But in order to make this L sub r of theta as small as possible, it requires our model to kind of do two things simultaneously. The first is that the model needs to make the MSE as small as possible, so it's trying to minimize the error, but it's also trying to keep the complexity of the model small at the same time. So if the MSE is really small, but you have to have a very complex model in order to achieve that, the overall loss, L sub r, is going to be really large. So the idea is our model is kind of balancing how well it fits the data versus how complex the model is. And as long as we choose this r of theta function to be differentiable, then we can fit a model using this loss function, using the gradient descent algorithm as we've seen. All we need to do in order to actually do that in practice is write down the derivative of this r of theta function. I'll point out here that this alpha parameter has some positive number that we multiply with the complexity function. And it's often referred to as the regularization strength. So it essentially tells us what's the balance between the MSE loss and this complexity loss. So higher values of alpha means we care more about the complexity of the model, we have more regularization. Smaller alpha means we care more about the MSE than the complexity of the model. This alpha value is another hyperparameter that we'll have to go ahead and tune whenever we're working with regularization. So typically alpha is something fairly small, again, something like 0.01, 10 to the minus 2, 10 to the minus 3. But it's something that you can tune, and it does impact the performance of your model. Okay, so I haven't told you yet what we're going to use for this complexity function. You might be able to kind of imagine different functions you could stick in here, but a very typical sort of class of complexity functions are built on what are called norms. So a norm is some kind of function that takes in a vector and just measures how big this vector is. So it's like measuring the size or the magnitude or the length of a vector. So if v is our vector, the norm of a vector is usually denoted by this symbol here. It's like two absolute values around that vector v. This norm of v is some non-negative real number, again telling us like the size of this vector. It's got to be non-negative because negative lengths don't really make sense. There's a sort of formal mathematical definition of what a norm is. If you're interested, you can go read the Wikipedia page, but we won't need the formal definition in this class. Just think of a norm as the size of a vector. Okay, so let me give you some geometric intuition on what's going on here. Let's say we're working in 2D, so we have some blue vector v, and we can draw it as an arrow that looks like this. This vector v is made of two different components, right? It's sort of the size in the horizontal direction and the size in the vertical direction. So I'll call these v sub 1 and v sub 2. And together, v sub 1 and v sub 2 define this vector v. An example of a norm is called the Euclidean norm, or the L2 norm. And the formula for this is v sub 2. And we square all the components of our vector, and then take the square root of them. This is really just the usual formula for the length of a vector, and really it's coming from the Pythagorean theorem. So if this is my right triangle here, the length of this hypotenuse is just v1 squared plus v2 squared, and take the square root to get the length. So, this is just the usual way of measuring the size or the length of a vector. But we don't have to use that to measure lengths. We could do some stranger things here. So for example, we can use what's called the L1 norm. And rather than squaring the components and taking the square root, what we do is we just add up the absolute values of the lengths. So it'll be the absolute value of v1 plus the absolute value of v2. For a little bit of sort of intuition on what these distances or what these sizes are actually encoding, the Euclidean norm kind of measures the straight line distance between the origin and sort of the tip of our vector. In contrast, this L1 norm measures sort of the distance between the origin and the tip of this vector if I can only move along the axes. So if I can only move along v1 and then v2. I can't fly straight to the tip of this vector. There's a general formula for what are called LP norms for any positive number p, where we take the absolute value of our components, raise them to the pth power, sum them up, and then raise it to the 1 over pth power. So if you plug in p equals 1, you'll get the L1 norm. If you plug in p equals 2, you'll get the L2 norm. And different values of p essentially change how we measure length of vectors. And we'll see some more details and more illustrations of this in a little bit. But what we're going to do with these norms is we're going to use them to measure how complex a model is. So a parameter vector is, again, just some vector of numbers. And we can take its 2 norm, its Euclidean norm, to tell us kind of the size of that vector. So we square all of our weights in a linear regression model, say, take their square root, and this gives us kind of the size of that vector. And what I'm arguing here is that sort of the norm of a parameter vector is a good way of measuring how complex that model is. So, for instance, if we're doing quadratic regression on, say, a single feature, we have 3 parameters. We have theta naught, theta 1, and theta 2. These are the 3 weights in our model. And if all of these parameters are small, so theta 0, theta 1, and theta 2 are very small numbers, then the parabola defined by this function is pretty close to the 0 function, right? If these numbers are small, they're almost 0, then f is just approximately 0, no matter what x value we stick in. Hopefully this is clearly not a complex model if it just predicts 0 for every input x. And in this case, the 2 norm of this vector theta is also small because we're summing up a bunch of small numbers in this formula. And so again, my point here is that you can use norms to kind of quantify or measure how complex a particular model is with a particular parameter vector theta. And what we're going to do is we're going to use these norms as the complexity function in a regularized model. So here I've got that same formula for L sub r. It's the MSE loss plus a regularization term, where this regularization term is now going to be the p norm of our vector. And we can vary the choice of p. Most commonly, you'll see p equals 1 or p equals 2 get used, and these have special names coming from the statistics literature. Maybe 70 years ago these names came out. I have no idea what lasso stands for, so don't ask me. But the p equals 1 case is called lasso regression, and the p equals 2 case is what's called ridge regression. Okay, again, we can fit a linear model with these regularization penalties in scikit-learn. We've got lasso and ridge. And again, I'll point out that this regularization strength you can specify when you're fitting these models. So it's another hyperparameter that we'll need to tune using this train validation test paradigm. And oftentimes this regularization parameter can have a quite significant impact on your model performance. So it's important to do a good job of tuning this. Okay, let's see a couple of examples of what happens if you use regularization with regression. So let's say we have some true function. It's some sine wave plus some noise. We have only 30 data points, and we're using mean squared error estimated with a 10-fold cross-validation. The orange curve in each one of these plots is the true function that we're trying to model. The blue curves are the curves learned by a polynomial regression model, having a degree either 4, 8, or 12. And with no regularization, we see that clearly this degree 12 polynomial is overfitting. We've got a very complex fit to this data. It doesn't match the true orange curve. If we turn on regularization, let's say we're doing ridge regression, so we're using an L2 penalty, where the regularization strength is 0.01. And what you should see here is that even if we go up to degree 12 polynomial, fit that polynomial, it's still a pretty good fit to our data. So we managed to kind of fight this overfitting problem by changing our loss function, by penalizing complex functions. Okay, So to illustrate what happens kind of under the hood in these models, if you look at the coefficients of the models that you learn with no regularization, you see these are huge numbers. We're fitting very complex models. If we turn on regularization, these numbers get quite a bit smaller. We get less complex models. Okay? If we use L1 regularization, something really interesting happens. A lot of these values now turn to 0 for some reason. And so maybe let me ask you guys if you have any guesses of why would L1 regularization make a lot of these parameters 0? It's a hard question. Okay, in the interest of time, I'll give you the answer, but hopefully you had kind of some intuition of what's going on. So if you use an L1 penalty instead of an L2 penalty, it's often called sparsity inducing, in the sense that it makes a lot of the weights in your model 0. So, let me mislead you for a second here and say, instead of using the usual MSE with regularization, let's consider a really closely related optimization problem where we want to minimize the mean squared error subject to this constraint that the one norm of my parameters is at most 1. So it's like doing this regularized MSE, but it's now a hard constraint on the size of the vector versus just kind of a soft constraint as in standard regularization. There's a really nice geometric picture for why L1 regularization leads to sparse outputs. So there's a lot going on here, and we'll break down what's happening. So these contours up here are the contours of the MSE loss function. So this is this bowl-shaped loss function that we've seen a few times now. If we just do unconstrained optimization of this loss function, the parameters that we would learn would be at the bottom of this kind of bowl-shaped function. This is just fitting a model using MSE. What I'm plotting here in the blue diamond is what's called the unit ball for the L1 norm. These are all of the vectors, all of the parameter vectors, whose one norm is at most 1. So to satisfy the constraint here, that this norm can only be smaller than 1, our parameter vector has to live inside of this blue triangle. Therefore, in this constrained optimization problem, we want to minimize this loss function while still living in this blue set. And because this blue unit ball for the L1 norm has this kind of diamond shape, you're much more likely to hit the corners of this shape. And the corners of this shape are precisely where some of the parameter vectors are 0. So here, theta 1 is equal to 0 because it's on the vertical axis. In contrast, if we look at the unit ball for the L2 norm, if you kind of plug in that constraint into the function for the 2 norm, it's actually an actual ball, not a diamond. It's got a circle. And it's very unlikely that you're going to hit sort of the corners here, just due to the geometry of this unit ball. So, there is some nice geometric intuition here, and I really encourage you guys to go back and think more about this. I know it's a little complex. I'll point out that you can use other values other than p equals 1 or p equals 2. So these are the unit balls for different values of p, say p equals 1/2, or in this special case, p equals infinity. Don't worry about this slide. I'll kind of gloss over it for now. We're not limited to just using, say, L1 or L2 regularization. We can also do things like take combinations of these norms. So you can use, say, the 1 norm plus the 2 norm as your penalty. One of the problems that you might run into with L1 regularization is that it can lead to non-unique solutions. So the loss function you get out from MSE plus an L1 penalty is not convex anymore. It doesn't have a unique solution. But if you use this penalty, where you have the L1 norm plus the L2 norm, you'd get a convex optimization problem again. It has a unique minimizer. And so you can get both sparsity and a unique solution. And this is nice if you want to, say, interpret the weights of your model. You don't want to fit your model multiple times and get different answers with non-unique solutions. Okay, so let's quickly summarize what we talked about today. The first is that model selection is the process of deciding which model to use out of various possible choices. This is primarily important for tuning hyperparameters,